I do a lot of applications with these guys, and I've been using their linear parts for the last 20 some odd years, and they make linear dual transistors, NPNs, PNPs, low noise parts, FETs, and now, because Paul Norton and John Hall have ceremoniously released the 2SJ, now LSK 74 P-channel FETs, I decided that this year I would emphasize a little of the work that I was doing using the P-channel FETs. And I think the 109s are coming soon? Soon. So, and this is the guy that you want to go after for these parts.
Notice the target.
Sorry, there's a target back there. So what we introduced last year was an amplifier that had a combination of parts. One, a linear front end that was designed using the LSK 389 N channels. And we could kind of skip right to that schematic if you just walk up a few of these things here. Una más. There, no, back up one. There it is. There it is. That's what we were doing last year. And what we managed to do with the LSK parts was to show an application where we could use a differential pair operating in a what everybody knows is a normal mode, except I capacitor couple things, and the reason that I do that is so I can isolate the biasing string so I don't have to deal with DC biasing terms. So the upper portion of this amplifier was all N-channel field effect transistors all the way to the output. Nelson had these wonderful things that he was talking about, the vertical JFETs, which is what these are. These are 2SK60s from Sony from about 45 years ago that we had on last year's amplifier. And one of the reasons that I happen to like those is the same reason that he does, is that the transfer function through a load line happens to be a very linear function. So a linear input in voltage across a gate source resistor results in a linear transfer function owed to the speaker. In this amplifier, what we were emphasizing were the dual NPNs. This, in this case, a full Wilson mirror, so that I could take any current and replicate it precisely on the other side without artifacts, and to have the noise present in both arms in sync and in common mode. The advantage of that is that by putting a current source in dual across this pair, differentially I end up with a pair of noise sources effectively in parallel, and can produce a fairly low noise differential stage feeding into this, which is, you can say it's a cascode transimpedance stage. This, going in, each one of these gates is sitting at a virtual ground. And so the drains of these FETs are held at a fixed voltage, and the gain then becomes the GM of this differential stage times these feedback resistors, and this entire loop gain of this stage is about 50 dB. That then went differentially into a pair of SITs again, and then SITs on the output, okay? And then there's a DC servo loop just to keep the balance between these two FETs to a level where the output would be within about 10, 20 millivolts of ground. Let me go backwards. Years ago at Linear Systems, back up some more, we were producing devices like this, like the ones that he was just talking about. And these pieces are in fact very linear, and in small signal end up the same as any other thermionic triode. And the problem that we get into in using these parts is, one is availability, and two is the cost, because the total demand for these types of parts is relatively low. So we have to go to standard parts or standard silicon fabrication processes in order to build an amplifier that sounds as linear as a all triode feedbackless amplifier. It has an inherent damping coefficient as a function of the resistance of the load to the resistance of the driver. So what we do is we use things like linear FETs and linear transistors and linear MOSFETs and the types of MOSFETs that were used in this year's amplifier. Last year was a part that's not available. And in fact, a lot of people complained about the fact that I had built something that we demonstrated that couldn't be reproduced. So I thought, okay, well, this year we'll build something that can be reproduced, and reproduced using existing manufactured product. So if you go forward, there. Okay, this monstrosity, on the initial inspection of this circuit, you could say that this is overly complex to do the job of amplifying a signal by 30 dB. But in fact, it's a very, very simple circuit. Do you have a pen? I don't have a pointer, so I'll use a pen. Thank you, bless you. Can everybody see this okay? Is that in focus?
Yes.
Is? It doesn't look at it. All right. So what I decided to do is to build an amplifier that, and unlike last year's contribution, where the audio path and the bias management path were in two different planes and completely isolated from each other. In this case, this is an amplifier where both the bias management and the amplifier are integrated into the same path. And so we could look at and I broke it down into sections. Forget the attenuator, we all know what that is. There's a differential stage, a very John Curl-esque kind of thing, and a set of gain stages that drive an output. And what we did here is created, first of all, again, using the linear parts, a full Wilson mirror in P and N complement, so that with a single resistor coming from regulated supplies, I could set a single current that would then propagate uniformly and evenly through both sets of rails to the output. So that current that's generated by the single resistor into these mirrors becomes the exact same current on this side, and these little MOSFETs here are simply being used as voltage buffers so that I can keep the voltage across the mirrors relatively low, right? And keep the mirror linearity extremely high. And these two current sources then, from a minus rail, conduct over to an N-channel differential amplifier and down to a P-channel differential amplifier, feeding into a cascode, which is biased up to place a fixed voltage of about 5 volts across the differential stage, keeping the noise low and the strain on the drain to gate voltage in what could be called a sweet spot for noise. And so we have a differential stage, cascode, and then again the voltage buffers, the MOSFET voltage buffers, and even though there's noise on the gates, since what's coming out of here are currents, that voltage noise on the gates of the MOSFETs does not contribute to the output voltage that's going to end up on the speaker. So here we have the mirror, we have a differential stage, cascode, and differential currents coming out on top and on the bottom. Then it goes into this nightmare. And this nightmare is actually a very, very simple thing. If you look back at the Wilson mirror circuit here, and you look over here, we have the exact same Wilson mirror right here and right here. And these are simply mirrored across the rail from each other. So what's below this rail and what's above this rail are identical. Okay? And this Wilson mirror, in semiconductor technology, in chip design, oftentimes current multiplication is required to produce gain stages and biasing throughout an amplifier. And in audio design, we don't have the luxury of having the guts of a chip available that can produce truly linear current transfer functions. But with a Wilson mirror arrangement, I can now take a single mirror and duplicate it down the line with parallel equivalent devices and create a 10 times multiplication of the current that comes in here. Precisely. It's like having a transistor with a beta of 10, but no artifacts from the emitter base junction. So all the little square law terms that become an interference in creating a truly linear audio signal replication, the interference goes away because what I put into this mirror comes out exactly 10 times that current. And so now I'm coming in with a couple of milliamps here and a couple of milliamps here, and I'm coming out with 10 milliamps here and here, and you see these MOSFET buffers again. I have a habit of these. And I stick them in there just to make sure that these mirrors all have a restricted controlled voltage across them, so that I can keep them again in the low noise sweet spot operating range of those transistors. And then it goes to this very curious stage here. If you step up one, this is the front end expanded a little bit so that you can see the mirrors, the differential stage. I've biased the gates up here so that I've got a fixed voltage across these FETs. These FETs track the voltage across this one by bootstrapping a voltage strung from this rail through a divider. Okay, next one. The mirror, this is one of the models that I was running for the mirror before we built this thing. And so we have a current source feeding this mirror, feeding a multiplicity of the same mirror going through buffers and then to an output. The next one. And this is where the mirrors meet the speaker. I now have two differential currents from the positive rail, and I have two differential currents from the negative rail. And because I happen to believe that there's no such thing as a complementary transistor, because transistors have in P channel and in N channel different types of conduction mechanisms. One is a majority transport electrons, and the other one is predominant of holes. And electrons travel as a function of the holes in that part. So it means that the areas of the dies for a P channel and N channel are going to be approximately 3 to 1 difference for the same amount of current going through. And as a result of that die area change, the capacitances related to P channels and the transconductance of the areas are going to be very different. And these things are always adjusted very carefully in what are called complementary parts by the rearrangement of die sizes, doping concentrations, and depth of depletion or depth of diffusion. And when that happens, you can get kind of close, but you can never really get a true P or N complement device. So because I'm at war with complementary devices, which is why last year I did everything in N channels, it's sort of like building tube circuits, with which I also am very familiar because it's a habit. These types of devices can be employed on both rails, P's and N's, in this arrangement by taking a P channel and referring the current at that gate to source to the plus rail from the minus end. And I can take the N channel and generate a gate source voltage from the plus end so that this arm and this arm are in sync and counterphase to these two arms, right? So now what I've done is I've taken an N channel and a P channel and strapped them with the oppositely arranged N channel and P channel, excuse me, and put a complementary device of each flavor on each rail. So that now the nonlinearities that are inherent in doing a complementary output drive tend to wash out because now they're identical, right? What it takes, however, to do that is it takes a couple of mirrors. So we have, in the beginning of this, we have a current mirror generating currents that go into a set of differential amplifiers that then go into another set of mirrors that then mirror out and generate the gate source voltages for all of these parts. Each one of these parts were from Magnatech in England. They're lateral MOSFETs, and the lateral MOSFETs have gate capacitances that are about 1/5 that of a vertical JFET or vertical MOSFET. And the other kind of cool thing about these transistors is that they have a threshold that's very close to 0 volts. And the transconductance of these devices is about 1 mho. So I can say that for each volt that I have on that gate, I'll get approximately 1 amp of current at the output. Now the difference in the gain between the N's and the P's, because of this business of trying to match semiconductors to be like each other, you never really converge. So the P channels have a slightly less gain than the N channels. So the way we make that up is we say, okay, we've got balanced currents here and balanced currents here. We'll simply change these gate resistors for the P's in those positions to a little bit higher value so that for a given current I end up with 1 amp out per volt, right? With 1 amp, that now for a pair of milliamps at the input gives me a pair of 10 milliamp currents out here times 100 ohm resistor, if they were equal in each arm. We'll give at 40 milliamps, I'd have 4 amps out there, each, or 8 amps, right? So this amplifier that I built, which happened to have blown up last night because of a terrible thing, I was working on it and I was biasing it up, and I had it up to around 200 watts in bias, and then all of a sudden I saw this little flash lamp go off like a flea was taking my photograph. And it was one of those particles that happens in assembly on a board, and it shorted out one of the arms of the amplifier, and it made some of the most mysterious sounds I've ever heard come out of an amplifier, and then it went down. But before that, it was a magnificent sounding piece of work that I really wish I could have showed you today, because all of this is nice in theory, but it's really the hearing that makes a difference. When I ran the models on these things, and I spent a little bit of time trying to refine what was the difference between this and a vacuum tube triode amplifier, or this and last year's amplifier with the SITs and the differential cascode transimpedance stage. What I found was this actually outperformed last year's work remarkably well. And if you looked at the input in the model systems that I use Linear Technologies LT Spice. I don't know, anybody in here use that? It's actually a very powerful and wonderful tool. You can take a look at the artifact distortion profiles in the feed voltages and what comes out, and they track like a bomb. And so when you back out all of these error terms in the two models, you find that the intermodulation distortion, which is the one thing that separates what you hear in this room from the sound of me being reproduced into this room. It separates those two into audibly true or not true to your ears when you close your eyes. It's not the harmonic distortion, it's the intermod distortion, because that intermod distortion produces pieces of acoustic signature that's not characteristic of the original audio source. And because it's not, you hear, I mean, your ears are wonderful 140 dB resolution, monitors. And because of that, you can pick out small products that don't fit. It's like, where's Waldo? And when you hear that, you close your eyes and go, yeah, well, that's reproduced. That's the intermods. And the object of the game in building any of these amplifiers is to try and seek a path, and like Nelson says, the simplest path to getting to a perfectly linear transfer function, nearly a wire with gain, from the input to the output. And so my focus in building this amplifier was to do something that was absolutely dead linear from input to output. So when I take this feedback loop back to the differential stage and rip it out, it should still be linear. It turns out it was. And the entire open loop gain of this amplifier, model-wise and predictably, is 60 dB of gain. With the feedback in here to the amplifier, it's a 30 dB amplifier, right? Which means that the transient response and the intermod characteristics on this type of an amplifier structure would be very, very, very clean. And the reason it would be clean is that you're not correcting for nonlinearities in gain throughout the entire signal path the way a classic textbook audio amplifier, you get a differential stage, and you got a little GM stage, and then a voltage follower out here, and then you look at the reverse transfer function of the load and the complexity of that load going in through the emitter, turning into a variable base impedance that walks all the way backwards through the amplifier. And that all of that is actually corrected in part by loop feedback. But loop feedback can only be compensated and linearized for a few frequencies at best, but not through the complexities of what happened in 3 and 4 and 5 tone intermod distortion type tone tests. And that's what, you know, and in each one of these amplifiers, typically what I do if I want to seek out an amplifier transfer function very quickly, I'll use 3 tones at the input, a very, very low tone, a mid-tone, and then a high, something around 7 kilohertz. So something around 70 hertz and something up around a few hundred hertz, and then 7 kilohertz. So I can see all of the intermod products around those arms. And when you start seeing all of those lobes, at least in your models, and then audibly when you hear it, go away, then it is Memorex. And so, let's see, what's the next slide from here? This is another type of amplifier structure, and unfortunately it doesn't use any of the linear systems parts. But this was a device I designed. I'm having this put on PC right now. And each one of these transistors is a 3-cent transistor, like a 4400 or a 4403. And this is, you know, again, these are all complementary parts. And this is a self-bias structure similar to a thing that I frequently refer to, maybe not in this talk, but a thing called a Folks buffer that was developed back in 1952 by Bob Folks at General Radio Corporation. And this is the Folks buffer right here, and then this is the Folks buffer on steroids. And what this amplifier does is puts out 30 watts using about $3 or $4 worth of transistors, right? And one of the cool things about doing something like this is that all of the distribution of gains and characteristics of the transistors tend to average out when you throw all of them into a bucket like this. And this was an experiment, this is a thought experiment just to see if it was possible to build an amplifier using junk out of the junk pile. And it turns out that it actually does work very well. It has a little more crossover distortion identifiable in the intermod analysis, but still this is operating very much in a Class A form. Everything out here is biased to a current that's equal to twice the maximum current that will be delivered by the amplifier, right? So if you say, well, what's the definition of a Class A amplifier? Well, my definition of a Class A amplifier is one that once you've put a wattmeter onto the line cord and you've measured the amount of power that it's drawing at stasis, and then measure the amount of power that it's drawing at full bore, you shouldn't see any change. Because really the amplifier should be, ideally, steering current, much like a power steering unit, from one side to the other, but the reserve should always be exactly the same. And this type of an amplifier structure, as well as the one that we were just lamenting its destruction, this also is one of those devices where in the output structure I had, have this thing designed. You'll see the big heat sink on the back of it. designed for a 3 amp idle current at plus minus 48 volt rails. So this thing's sitting there cooking at a few hundred watts. You say, well 3 amps, well, what does that mean? Well, that means that I can take one of these rails, and as I back down one of these arms of the amplifier to 0 current, this one can dial up to 6, right? The total power consumption out of that power supply is going to be about the same. And what I'm doing is I'm simply steering current. And of course, what's also true about any of these amplifiers, and it's not immediately obvious until you build a few of them and listen to a few of them, is that the capacitors are the return path for everything that comes out of this amplifier. It doesn't go into Con Edison. And so all of the capacitors that you use for an amplifier like this should be of the very, very highest grade. What I have on this amplifier in there was 40,000 microfarads per rail, right? So into an 8 ohm load, I really don't have to worry about anything including the lowest frequency of the timpani, because it's going to come out with only a fraction of a dB loss by the time I get through the middle of the note, right? So let's see, what's the next one from here? And this is what you really want to thank the people you live with, like your wife, for allowing you to do, because this is our breakfast room table. And the next slide is what the breakfast room table looks like when you're going through a project like this. And so my thanks is to Suzanne for allowing this to happen, but I think this will be the last time I can do this. These are also the speakers that we built for this. These are Fostex. They have a fairly good frequency response from 30 to 20,000 hertz if you build the cabinets in just the right way. And these aren't quite the right cabinets, but they're getting close. So let's see. Go to the next one. These are by the way. I love what Nelson was talking about. These are the Yamaha parts out of the B2 amplifier. These are the FETs that were built back in 1974, I believe. And these are the P channels. These are the N channels, and they do look, feel, and operate exactly like one big damn triode with a transconductance of about 1 mho. And they're low mu type devices. They have a mu of about 2 or 3, right? But controlling these types of things from current sources, you end up with a very, very linear type of. Go to the next one. And I just wanted to show you the versatility of linear integrated systems. In the 1990s, we were engaged in a product to replace 12AX7s with a linear device, which was a static vertical FET, and it was constructed on a header with aluminum nitride insulating substrate, and then the dies were put on there and attached, and then this big can was put on there, and it was only big because it made it convenient to plug in and out of a 12AX7 socket, because if you make it too short and you put it into an MPEG guitar amplifier, you can't reach it again. So and then the next slide over here is, this was the transfer function for those metal devices. As you can see, this is very, very much akin to something that's around 1250, 1300 micromhos, which is what is the 12AX7. The gains on these were very close. They were about 3 dB lower than the 12AX7, but still sounded the same with one change. The slope in these curves, if you look at the slope in a 12AX7, these curves kind of lay out a little more, because as you get toward cutoff, the effective plate resistance goes up. In the silicon versions, this slope stays more constant through the entire cutoff region. And so when you replace a vacuum tube with a silicon device that has the same effective transfer function, you hear something very marvelous. you don't hear the frequency shift at the wide range of amplitudes. That sort of a frequency distortion that you hear in a tube amp. Some people think that's nice because it's warm. What you hear out of an amplifier like this is you hear a very clean, nearly intermodulation, distortionless transfer function. And, you know, again, this is what I consider as well the ideal for a load line. What we strive to do is to try and duplicate this using standard transistors, and we can come so damn close that I hope in the future that I can put these things side to side and show you that you can't tell the difference. Are there any questions?
What's the big thing on when you were on the 570 curve tracer, what's the device?
Go ahead. What is that? No, the other way. Other way, other way, other way. Keep going, one more. That is a 7027A, built-in silicon. That's a, you know what those are, right? Okay, this is a 6L6 on steroids, and that's the transfer function for the 6L6. One of the things that's also, by the way, when you simulate or emulate a vacuum tube using semiconductors, by the way, this also uses a lot of linear integrated system parts in here, JFETs, to produce, along with some big lateral MOSFETs, high voltage lateral MOSFETs, to produce these curves. And when you look at the curves across here and you look at the steps, Mike, they're incredibly linear. So when you put a load line through that tube, even though it's a pentode and it's a current source, just like any other FET, the beauty of this is the transfer function in terms of current versus input voltage. And so the load line through this, and unlike a normal 6L6 or a 7027 or a 6550, you don't have that tetrode nonlinear wrinkle in the beginning of the curve, okay? And so when you get down to the low volumes, and in fact even into the peaks, into the high volumes, where Joe Satriani would like to run, you'll find that this tube has a much more faithful reproduction of sound with low intermod distortion than any of the tubes that it replaces. And so this device is an experimental thing that I was doing because I am nuts. And I had a machinist make up these wonderful halves that were mirrored so that we can make these things in an extrusion process. And then up through the center of this are bosses where are mounted things like lateral MOSFETs and linear integrated systems parts and resistors and diodes and all kinds of monstrosities. And in fact, when you modulate the screen up and down on this silicon replication, the plate current goes up and down exactly in the same proportion as a 6550 or a 7027. So the screen, so you can take this and not only use it in triode mode, right? But you can use this in pentode mode, or you can put it on a 40% tap screen transformer and use it in an ultralinear mode, right? It is possible to do this, and you can do all this stuff in silicon. It takes a little bit of work, but the results from something like this, there's only one of these left. The other one has been torn apart so many times for demo that it looks like shards anymore. But you know, this is another one of those things, if there was ever an interest in it, this would actually be an interesting thing to build. Because this allows you to take something like a guitar amplifier and literally run it forever, along with anything else that you do that you replace with silicon in these parts. So anyway, what is that? That's a 7027. In answer to that question, are there any other questions? Yes.
As a tube guy, I have to ask.
Then I love you.
Your data is marvelous. The numbers look great. How does it sound?
Gorgeous.
Cool.
Drop dead gorgeous. Yes. On on those things that we called the voodoo parts, you notice it's still left over on my curve tracer. The OAX7s, they were it was a company that I launched back in the mid-90s, and it died on the vine like many companies do. Lack of investment and interest and all that. But for the parts that we had, when we substituted these and demonstrated them for PV, for St. Louis Music, for Soldano, all of them hands down said, yeah, that's the right thing to do. Win. And the market, unfortunately, although there was, and Marshall was another one who expressed an interest in these types of parts, but the backers that I had at that time were more into telephone parts than they were into vacuum tubes. So telephone parts, yeah. Your cell phone is a result of, because this project died, you have better cell phones. So you know, the sum total of the argument, if there could be made one, is that the intermod distortion characteristics that you find attractive and useful in, I'm ready to go, attractive and useful in a vacuum tube amplifier can, in fact, with a little bit of work, and not much, be replicated by silicon in what may not be immediately recognizable amplifier architectures, but still valid. And yes?
Kirkwood, I wonder about your larger, you know, one of the things that
What, this thing?
that problem long ago with the 12AX7.
Yeah.
The thing about the 12AX7 and rock groups and you know, is the roadworthiness and stuff. It seems to me that a 12AX7 will last pretty well on the road, and you have a big tube like a 6L6 or whatever that is.
They didn't, and the reason that the big tubes wouldn't last as long as the lower ones are always running at a constant cathode temperature and a constant cathode current.
What about just roadworthiness?
Roadworthiness,
Being on a truck for,
the bigger they are, the harder they fall.
well, I mean, that means the sooner they fall, or the...
Now, when you run 6550s, L6s, EL34s, anything, at high plate currents so that you can get more linearity out of them, and you come up here at full volume, overdrive, at the top of the neck, peeling away, you are not only driving the tube into full conduction, trying to strip that cathode of all of the oxide it has on it, but you're also extending the voltage range of the tube into regions that it doesn't belong in for acceleration because of the leakage reactance in those transformers. And it takes those tubes and beats the living crap out of them. You won't see a 12AX7 going through that type of abuse. But that's, you know, that's the difference between, you know, roadworthy 12AX7, no problem. Roadworthy 6550, not on your life. One of the other problems that you see with the modern 12AX7s is that the plates, you'll notice, are now about 1 centimeter tall instead of about 1.5 centimeters. And the grid to plate, the cathode structure has been changed a bit so that the actual frequency range that those tubes can operate in is 1.5 to 2 times higher than it was for the original 12AX7s. The Miller capacitance is less. And so, because the bandwidth is so much higher on 12AX7s, you'll plug in something from Shugong or from JJ or anyone. And you'll say, oh my God, the amplifier sounds horrible. It's because the amplifier is usually oscillating at 300 megahertz, and you don't see it because your scope doesn't go that high. And while the tube is busy spinning away at radio frequencies, the audio gain then suffers from the conductance shunt of the high frequency. And so once you've suppressed the high frequency oscillation in that tube with a ferrite in the cathode to kill the gain, or with a small amount of capacitance from plate to grid, it suddenly stops, and that damn tube that sounded horrible sounds great again. So I don't know if you've noticed this, but if you get a really high frequency scope, many of the amplifiers that are out there were not designed to handle the parasitic characteristics of the new tubes. So, and that's a discussion that could go on for hours, because I do amplifier repairs for people, and I have to run across some very, very squirrely problems in this line. So anything else going on? Yes.
You mentioned Marshall.
Yes.
Did you actually produce the EL34 set?
No, I did the 7027 because it's the absolutely worst tube to try and replicate, because it has the highest plate voltage and the highest peak currents. The EL34, this actually is very close to an EL34, except that the EL34, you'll notice that it slopes more in the beginning, right? That resistance is what makes the Marshall amplifiers sound a little softer and what some people call sweeter than a Fender.
Yeah, and how much did those devices go for a pair of?
What, this thing? Of the silicon version?
Yes.
They were never produced.
Oh, okay.
No, this is an experiment. The reason I bring this up is that this was done using silicon, and you could reproduce a pentode with screen grid control and have the full output voltage, because IXIS and people like International Rectifier make 2,500 volt devices now. So those, in combination with other support circuitry of extremely linear parts like what these guys make,
As a point of history,
you can build them.
maybe other people could fill in on this. CBS Labs spent, I don't know, whether it was millions, trying to
So did Teledyne.
achieve it, and Leo Fender bought his company back.
Yeah. Now, Teledyne tried, Groove Tubes tried to do this.
So it's extremely.
It's a very difficult problem to solve. However, it's not as difficult as you might think. So what I'm thinking of doing is there's a number of things that I've discovered about the linear parts that I can use in these types of devices that later on this year I may be publishing. So if you're really bent on self-destruction, you too can build output tubes. So we have another speaker coming up here, I believe. I'm over time.
Go visit him at the booth. Ask him all the questions you want.
Peace.